Hi everyone. So I thought I'd quickly record solutions to the two questions at the end of Activity 1 in Unit 2. You should try them first before checking these solutions out. So if you haven't tried them, go ahead and give them a shot, and then come back here and take a look at how I solve them. So the first question is, you're going to play the 4-dice roller game in the Games Fair, and the two questions are: explain how a tree diagram could be used to explain how many total possible ways, N of S, there are to roll 4 dice, and then using the slot method in multiple cases, calculate the probability that you would roll 3 sixes, excuse me. So first of all, the tree diagram for 4 dice. So I took this video clip, or this image from an online search. So here's the tree diagram for 2 dice so far. So when I roll the die once, I've got 6 outcomes, and then when I roll the second die, off of each of those 6 there will be 6 outcomes. So if I roll just 2 dice, we know that we have 6 times 6, or 36 outcomes. Now if I wanted to, I could extend this for 4 dice, but we could see quickly that it becomes unwieldy pretty fast, because the third level of this tree diagram would require me to draw 6 branches off of each of these outcomes for the second die, and so that would represent the third die roll, and then lastly the fourth die roll would be 6 branches off each of those. So obviously a tree diagram would be very unwieldy and take a long time, very messy. So the easiest way is to use what they call the slot method in the lesson. And so think of each slot here representing how many outcomes there are for each die. And so for the first die, as we said, there was 6, and the second there are 6. And so that's how we got 6 times 6 is 36 here. So after 2 dice are rolled, we have 36. But then for the third die, there's also 6 outcomes. And then lastly, for the fourth die, there are 6 outcomes. So when we multiply each of those outcomes, this is the fundamental counting principle from last unit coming into play here. There are 6 ways for the first outcome to occur, and 6 ways for the second outcome, 6 ways for the third, and 6 ways for the last. We have a total of 1,296 possible outcomes when you roll 4 dice. Alright, so now let's tackle the second part of the problem. Using the slot method in multiple cases, calculate the probability that you would roll 3 sixes. So probability, again, when you boil it down, is the number of ways my event can happen, which is how many ways can I roll 3 sixes, over the total number of outcomes. Well, we've already got the total number of outcomes. The total number of outcomes, which is the number of outcomes for our sample space, or sometimes that's called the universal set, is 1,296. That was the total number of rolls for 4 dice. Now the tricky part here for figuring out the number of outcomes for our event is that for us to roll 3 sixes, that can happen in different ways. That's why there's different cases. So over here on the right, I'm going to try to build these cases. So we could get so let's think of our slots again. So I'm going to draw 4 blanks. And for example, we could get 6 on the first one, 6 on the second roll, 6 on the third roll, and then I'm going to put a question mark for something else here on the last roll. Same thing, it could happen in this way. We could get 6 on the first roll, 6 on the second roll, but we can get the unknown other number, not a 6, on the third roll, and get 6 on the last roll. So that would satisfy getting 3 sixes, because we have 3 sixes on the first, second, and last roll. Or it could happen this way. We could get a 6, then something other than a 6 on the second roll, then 6 and 6 again. And there's one more way this can happen. We could get the not a 6 number on the first roll, and then 6 on the second, 6 on the third, and then 6 on the last. So there are 4 different cases. Now what we have to figure out is how many ways can these happen. So let's go back to our very first one. 6 followed by 6 followed by another 6, then something that is not a 6. So for the number of ways this can happen, well, I've got a roll of 6 on the first roll. Well, there's only one way for that to happen. So I could think of this as 1 times, I got to get a 6 on the second roll. Well, that's 1 again. There's only one way to get a 6. And then another 6 on the third roll. Again, only one way for that to happen. Now, the last roll, I got to get something other than a 6. So since there's 5 things that are not 6s, I'm going to multiply by 5 this time. Now, notice that's not 6 because we want to exclude getting a 6 here, or else we'd get the possibility of getting 4 6s. So this works out to 5. Now, if you work out the remainder of the other 3 cases, you'd see that it's exactly the same thing. The only thing that's changing is where are we putting that 5? Is it in the third, the second, or the first location? So each of these has 5 ways of occurring. So the total number of ways that our event can happen, n of a, is the sum of these 4, which is 20. There's 20 ways that I can roll 3 6s. So the probability that I roll 3 6s, and I should have defined my event A, I should have said let A be the event that I roll 3 6s, is 20 out of 1,296. And this works out to about, when we change that into a decimal, it's 0.015432. So get a lot of decimal places in there. But if I change that into a percent, that's about 1.5% chance of that happening, which is probably kind of what you feel. Chance of getting 3 6s when you roll a die 4 times is probably not very likely, but so there we have it.